In this video, we are going to introduce our last conic section, which is the hyperbola. And as I've said at the beginning of my other videos on conic sections, we are defining these as geometric objects. We are not defining them as functions because they are not functions. So just like we did for circles and for parabolas and for ellipses, we're going to define this in terms of distances. So here is the definition of a hyperbola. I pre-wrote it so we could just read through it. A hyperbola is the set of all points in the plane, the difference of whose distances from two fixed points f1 and f2 is a constant. So I just want to underline the word difference here. And then I want to point out that this definition is similar to the definition of an ellipse in a lot of ways. Once again, we have two foci. We once again label them f1 and f2. And once again, we define the hyperbola in terms of the distances from every point on the hyperbola to both of the foci. The distinction is that with an ellipse, we look at the sum of the differences, and here we look at the difference in the distances. Okay, so for the purposes of this example, this is not going to be a super carefully planned out example. I'll just kind of sketch out the basic shape. So we'll have a hyperbola like this. So it has two lobes. If you remember, we get a hyperbola by using the conic section of a double cone, a cone kind of stacked on top of another cone. And so you end up with these two lobes. Like I already said, they should be symmetric. These two may not be perfectly symmetric, but for the sake of this example, we'll say that close enough. So then we have these two foci. So let's say this is f1 and this is f2. Okay, and I'm going to pick a point on the hyperbola. Let's just call it xy. And now let's look at the two distances to f1 and f2. So here is this one, and then here is the other one. Okay, so what I'm telling you is that if I call these, say, D1 and D2, and I look at the difference between D2 and D1. In this case, D2 is the bigger one. So I'll write it first, but really you could just use absolute value, and then you could guarantee that the distance is going to be positive. So D2 minus D1 is equal to some constant K. And what that means is no matter what point I take, so I can even take a seemingly much more far away point, and look at the distances to f1 and f2. And of course, the distances are both significantly bigger, but the differences between the two distances are going to be the same. So that is the idea of a hyperbola. Now, just like with an ellipse, I'm not going to go through the process of deriving the equation of a hyperbola, using the Pythagorean theorem and the distance formula and all of that. I'm just going to state the equation of the hyperbola, and we're going to walk through the particulars. But if you're curious about how the equation is derived, you're welcome to come talk to me in office hours, and I'll go into more detail. On the next page, I've drawn two hyperbolas. So these two are actually drawn a little bit more carefully, and I did so in order to sort of showcase some of the big and important properties of a hyperbola. So the first thing is, you'll notice that there are two shapes here, one that's oriented horizontally and one that's oriented vertically. So this first one on the left is one that we call a hyperbola with a horizontal transverse axis. I'll say more about it in a minute. And this one on the right is one with a vertical transverse axis. Okay. So now for the equation. So I'm going to go ahead and skip straight to the equation, and then we'll talk about the particulars. So the equation of the hyperbola on the left is x squared over a squared minus y squared over b squared. Okay? So let me label a few points here. So this point, kind of at the tip of the rightmost lobe, is the point a comma 0. This point at the kind of tip of the left lobe is negative a comma 0. Okay. And then this point doesn't seem like it's playing a particularly important role here, but I'm going to label it anyway. This point is 0 comma b, and this point is 0 comma negative b. So again, this point, these 2 points don't seem to be playing a super powerful role, so why label them? And for now, I'm mostly going to skirt that question, but in our next video that has examples and kind of solving specific problems, I'll go into a little more detail because that point comes into a lot of play when it comes to actually sketching a hyperbola given its equation. So now you'll notice that hyperbolas have asymptotes. Okay, this is why we talk about hyperbolas and in fact conic sections in general at the end of our time together, because we've talked about all of these things and we know what they are and we're comfortable with them. So hyperbolas have 2 asymptotes, and in the case of a horizontally oriented hyperbola, the equation of those asymptotes is y equals b over ax for the one with the positive slope, and y equals negative b over ax for the one with the negative slope. And so to finish the equation, we have x squared over a squared minus y squared over b squared is equal to 1. The last thing that I will say before I move on to talking about the foci is that this is a hyperbola with a horizontal transverse axis, and we can actually say more. The transverse axis is the line joining up these 2 points. So we can actually say in this case that the length of the transverse axis is 2a. Okay? All right, good. So the foci. So let's label them on our graph. We'll use some other color. So this point here and this point here. And they're on the same axis as the transverse axis. So in this case, they're on the horizontal axis. And so their coordinates are C0 and negative C0. And very similarly to the way in which we express C in terms of A and B for ellipses, we do so here as well. So C squared is A squared plus B squared. In other words, C is the square root of A squared plus B squared. Okay? So this is what it looks like to have a hyperbola with a horizontal transverse axis. And the equation is x squared over a squared minus y squared over b squared is equal to 1, where once again, a is half the length of the transverse axis. So now let's look at the example where the transverse axis is vertical. A lot of the labeling is the same. It's just what used to be played, the role that used to be played by the x-axis is going to be played by the y. In large part, that's the main distinction. So here, it's going to be these 2 points. So the ones kind of at the tip of the 2 lobes. So this is going to be 0, comma a. This one is going to be 0, comma negative a. And then just like I said with the the horizontal transverse axis example, there are also these 2 points that don't seem to be playing a huge role right now, but they will be playing a bigger role in just a little bit. Again, we have 2 asymptotes, and they are lines, so they have equations. So this asymptote with the positive slope, its equation is y equals a over bx. And the one with the negative slope, it's negative a over bx. So what's the equation? So you'll notice that the equation kind of lines up with what we would expect because everything is the same, just kind of the role of x and y seem to be switched. So this time it's y squared over a squared minus x squared over b squared is equal to 1. The foci, same thing. So the foci are on the inside here. So there they are, like so. And again, they're on the vertical axis, which means that we have 0, c and 0, negative c. And just like with the horizontally oriented hyperbola, c squared is a squared plus b squared. So c is the square root of a squared plus b squared. Okay? The last thing that I will say here, and that's going to mostly conclude our summary, is that in much the same way that the horizontal transverse axis had length 2a, well, the vertical transverse axis also has length 2a. So this essentially concludes our summary of kind of the basics of hyperbolas. We'll look at some examples in a future video, but for now this kind of sets the tone and we get the basics of what is happening with hyperbolas, what they are, and how they work.